Welcome back, Physical Science 20. This is the second part of HT 1.3. So we looked at how thermal energy is released and absorbed and how we calculate it. Now we'll look at the principle of thermal energy exchange. So the principle of thermal energy exchange states that when a warmer object comes into contact with a cooler object, thermal energy is transferred from the warmer object to the colder object until the energy is evenly distributed to both objects. In other words, the object with the higher temperature transfers energy to the object with the lower temperature until they both have the same temperature. If you use the quantity of heat equation to calculate the thermal energy released by a warmer object, so the Q equals mc delta T from the previous video, and we looked at the amount of Q absorbed by the other object, they should be equal in magnitude, so equal in sizes, but opposite in the direction of energy. So one is going to be gaining, the other one is going to be losing. So Q released is going to be a negative answer since the temperature will be negative because it's going down. The final temperature is lower than the initial. And the Q absorbed will be positive since delta T is positive. It'll go from a smaller temperature to a higher temperature. Concerning the law of conservation of energy, this makes sense. So we're assuming that there's no energy loss. So it's a complete transfer from one to the other. So thermal energy, like other forms of energy, can't be destroyed. It can only be transferred or transformed. So in this case, we're assuming it's going to be transferred. This conclusion assumes that thermal energy remains in the two objects being studied and is not released to the surroundings. So again, we're assuming it's a closed system and nothing is being lost. In most circumstances, however, some thermal energy is released to the surroundings. Mathematically, Q released and Q absorbed should therefore add up to be zero. So for example, if we lost 5 joules here and gained 5 joules here, of course, -5 is not equal to 5, but I know that if I take this and combine it together, I should get 0. So they're equal and they're the same size, but opposite in magnitude. So this is what we're going to use to compare the two. So of course they should, because one is releasing, the other one is gaining, so the net change should be 0. All right, so we'll look at an example here. Quite a few examples. You'll try some. And so if we look at this one, a 60-gram sample of metal is heated to 100 degrees C before being placed in 200 mils of water that has an initial temperature of 10 degrees. The metal-water combination reaches a final temperature of 15.6 degrees. So again, they reach the same temperature. And then determine the identity of the metal. So what is the identity? We can get that if we can find the specific heat capacity value of water. Because if you recall, in the last video we looked at this chart over here. If we can find what the C value for the material is, that'll tell us what the identity is. So we're going to break this off into two sections. We'll look at all the information concerning the metal, and then we'll look at all of the information concerning the water. Okay, so of course we're going to have to figure out the M, the C, the delta T. To distinguish one from the other, sometimes what I do is I write a little subscript. So the mass of the metal versus the mass of the water. To distinguish between the two M's, I'm just going to call this little m for metal and this little w for water. So the metal, we're told, was 60 grams. And of course, we have to have that in kilograms because our specific heat capacities are in joules per kilogram degrees C. So of course, divide that by 1,000 or move the decimal 3 places to the left, and I get 0.0600 kgs. The specific heat capacity, as it pertains to the metal, that was a question mark. I don't know what it is. That's what I'm going to be figuring out. TI, the initial temperature of the sample was 100. And when it's combined with the water, it reaches a final temperature, I was told, of 15. So change in temperature, T final minus T initial. 15.6 minus 100, that gives me negative 84.4. And it makes sense that it's negative, right? Because the metal is losing thermal energy. MW, so the mass of the water. Now, we weren't told the mass, but we were told how much volume we have, 200 mils. And as I say in this note here, the density of pure water is 1 gram per milliliter, which means 1 milliliter is 1 gram and vice versa. So 200 mils is actually 200 Gs. And of course, yes, divided by 1,000, move decimal 3 places to the left. 0.2000 kgs. The specific heat capacity of water, the CW. Oops, let's do it like that. So if I look at the specific heat capacity of water, 4.18 times 10 to the 3. So with a little bit of magic here, I fixed this over here. So it's going to be 4.18 joules per kilogram degrees C. And I missed out the 1 times 10 to the 3. So it's a little more magic. There we go, 4.18 times 10 to the 3 joules per kilogram degrees C. The initial temperature of water, I was told, was 10 degrees C. Then when the metal is put in there, they both reach a common temperature of 15. So the change in temperature will be TF minus TI, which is 15 minus 10. Let's see, that was 15.6 was the final. So that's going to give me 5.6 degrees C. All right, so I have all the information I need at the start. So I can use this idea over here, the principle of thermal energy exchange. Q released plus Q absorbed should add up to be 0. Because if I bring one to the other side, it's going to be negative 5 is equal to the negative of 5, which is negative 5. So it all works out. So here the released part is going to be my metal, Q metal. And my absorbed is going to be my Q water, QW. And of course, from before, Q is equal to MC delta T. So Q here is equal to mass of metal multiplied by C of metal multiplied by delta T of metal. So it's basically using this, converting Q into MC delta T. And do the same thing with water. MW, CW, delta TW. Okay, and then just substitute everything in. So my metal was 0.0600. CM, that's what I'm figuring out. T metal, negative 84.4. And then my water, 0.2000, specific heat capacity of water, and temperature change of water, all equals 0. So 0.06 multiplied by 84.4 to the negative, that gives me negative 5.064 multiplied by C metal. And then 0.2 multiplied by 4.18 times 10 to the 3 and multiplied by 5.6. That gives me this. Then to solve for C, the CM term, I have to isolate this first, which means this plus 4681, I'm going to have to subtract it. So we get this, and then of course divided by negative 5.064, divided by negative 5.064, Cm is equal to 924.486. So So I could round that off to, let's see, 3 sig figs. 924. Or if I put this in scientific notation, which is what they are on the table, place the decimal here, 2 places to the right. So 9.24 times 10 to the 2 joules per kilogram degrees C. Then if I look at my table, let's see, does anything match up with 924 or 9.24 times 10 to the 2? There it is right there. 9.2 times 10 to the 2, or that's just simply 920. So it looks like it's going to be aluminum. Therefore, Cm is aluminum. All right, so that's how you do that. So what you may want to do is try the next one. There is a density part of that. You're going to have to convert milliliters into grams for water, but you should be able to do that. So go ahead, try that next one, and then come back, look at the next video.